So hi everyone, I'm Ralf. I'm a third year PhD student at TU Munich, and I've also worked with Daniel in the past, and now I'll show you a work that we heavily used CRISP to deploy policies and to collect data. So I'll talk about our work on continual learning for vision language action models via autonomous adaptive routing and expansion. First, briefly, I want to talk a bit about my background. So I'm a PhD student since 2023. Before that, I obtained a bachelor at University Erlangen-Nuremberg. Then I was at Bosch and EPFL for internships. And recently, I was also an intern at, a visiting researcher at ETH Zurich. Okay, so continual learning. I think the problem is quite easy to explain. We want to have systems, robots that continually acquire new knowledge over time, like humans. Let's say you have a robot that today you want to empty your dishwasher in your kitchen. Then tomorrow you realize, okay, actually I don't want to do groceries anymore. My robot should also learn to do this for me. And maybe a year from now, the robot is in another person's home. Maybe someone else bought the robot, and that person then suddenly wants the robot to clean their specific windows. So, I mean, in these kind of scenarios, robots really need to continually learn and acquire new capabilities, and they should do that without forgetting what they have previously learned. So this is the key point in continual learning. And this is actually a very long-standing problem. So there has been work by Sebastian Thrun more than 30 years ago on lifelong robot learning. Back then, I think they were mostly thinking about navigation, but it's still an open challenge, especially how to do this with large-scale robot foundation models. So the issue that I was mentioning before is that we want to avoid when we continually learn new things is forgetting. And that means basically that when we have, let's say we have any machine learning model basically that's first trained on task A, then performance increases a lot. And eventually we now switch basically our objective to task 2, task B. And if we train on task B, then we will eventually get very good at that task, but we will just override the representations that were relevant for task A, and then performance will degrade very rapidly. And we don't want to have this. The goal is basically to have the blue curve staying up here. That's the goal. And to have this maybe not just for 2 tasks, but for many multiple tasks. So the method that we propose is called CLARE, which stands for basically what I the title that I showed at the beginning. And so we do continue learning for VLAs, which means these are robot foundation models that take in language, images, and usually the state of the robot as input. And in the end, they produce actions to move the robot in the workspace. So, I mean, we also study the common case now that we have some large-scale pre-training data on which we pre-train these models, so that they have some general capabilities of visual understanding and maybe some ideas of how robot actions typically look like. And then basically, during continual learning, the robot should iteratively learn new tasks without degrading performance on previous tasks. And basically, the method that we came up with is summarized here. I'll go into a bit more detail later. But this is kind of the setup that we have. First, we assume that we have a pre-trained policy, and then we want to continually learn new tasks. So main points of CLARE are that we avoid this forgetting that I mentioned before. That is also a parameter efficient method. So we don't just blow up the model with every new task we double the size of the model. That's not what we're doing. And it's also autonomous. So we can then, at this stage, we can deploy the policy and basically give it any of the tasks, and the policy figures out basically on its own which task it needs to solve and how to do this. Okay, so I mean, we are a university, so we wanted to study this problem at a compute scale that we can still manage. So we were not directly doing this for large scale VLA like Pi, but that was, I think, 1.5 years ago. So back then, we kind of designed our own smaller VLA which is basically like a multitask diffusion transformer with some pre-training. So essentially, as I said before, we have language, vision, and the state as input. They then we basically project all of these inputs basically into tokens, which are concatenated, and then we have linear projection layers that basically project these into observation embeddings. I mean, we don't need to understand all the details, but the key point is that we have these different inputs that are projected into some embedding space, and then we gather with time step embeddings, which is a thing from diffusion, but yeah, also not too relevant here. These then condition diffusion like a transformer, a diffusion transformer, which generates a sequence of actions. Yeah, but the main point is we have multiple, like it's a large neural network which has multiple modules, and basically these observations, they affect how the actions are being generated, because for different observations, different actions are optimal. So the main idea is that we want to not override the parameters that the model already has, because this would kind of degrade its great representations from pre-training. But instead, we want to store knowledge about new tasks in like specific adapters, such that we can kind of increase the capabilities of the model without degrading all the generalization that we have from pre-training. So the key idea is that we have certain modules in this BLA architecture that I showed before, to which we want to basically add these adapters in parallel. So the idea is that, let's say this is a certain layer of the neural network. For example, we saw that doing this for the like these linear projection layers that I showed before, that basically project the observations into embedding space. These were quite suitable for adding these adapters for storing new knowledge. And basically the key idea is that, let's say we have task 1. The model is supposed to learn task 1. Then we add an adapter in parallel to this module and train this adapter on the data that we have for task 1, such that we can, after that, add its output to that of the frozen BLA backbone to kind of steer the model towards how to actually complete this new task that it has learned. Because this module alone would not be able to complete the task. Maybe we have some rough idea of how to do it, but not like it would actually lack the precision to complete it. And for this, we need to train an additional adapter to give it this more fine-grained knowledge. So yeah, now let's say, okay, we have these adapters for new tasks. Now, when we actually deploy the model, we need to figure out which is actually the correct adapter that we should activate, because maybe after some time we have multiple of those. But in our assumption, or in our case, we assume that only one corresponds to the current setup. For this, we don't just train adapters, but we also train discriminators. Basically, these discriminators decide which adapter we should activate for the current task. So here we can see that each of these discriminators produces a loss, and then the discriminator that is kind of connected to the adapter with like the discriminator which produces the lowest loss decides which adapter we should activate. In this case, the discriminator here is connected to adapter from task 1. So in this case, as its loss is the lowest, we would activate adapter from task 1. Now, you might wonder, okay, so but why are these numbers different? Why don't we have an adapter for task 2? Well, we're also thinking that maybe some tasks are very similar to what we have already learned before. So maybe not for every task we need to add adapters to all of these layers. So because of that, we perform what you call dynamic expansion. So the network is only expanded basically when that's necessary, or certain layers are only expanded when that's necessary. So let's say we have a new task that we want to learn, and then in a certain, like these expandable layers, basically, let's say in this case, each of the discriminators that we have already learned would have a high loss, which means the new task has features that are very different to everything that we've learned before. In this case, we need to store knowledge about the new task in a new adapter. If that's not the case, if one of the discriminators produces a small loss, this means that the new features for this particular task are very similar to one that we already learned. In this case, we can just basically kind of remember, okay, when we see this like new task 4, or basically here in this case, it would be, basically it would be task 4. Here, when we have task 4, we can just use the adapter from task 1 because its features are very similar to the task. And so then we would just link the new discriminator to this already existing adapter. Yeah, so this is, I hope this was somewhat clear. We can also talk about this later if you want. But yeah, to not delay the pizza too much, I think I can show you some videos. Sorry, I think need to wait with like this to see how this actually looks like, or what this can actually do. So we have some real world tasks where we want to like learn one after the other. These are our manipulation tasks with CRISP. We collected the data and deployed these tasks. And you can basically see at the end, the same model can do all of these 5 tasks. So maybe to briefly pause here. So at this stage here, basically we have one model that can do task 5, but the same model, if you just change the language instruction and the objects in the scene, the model would just autonomously perform task 4, task 3, and so on. Okay. So yeah, I also show some more more qualitative analysis of this. So at the end, at the final stage, we have all these different adapters, and we were also wondering, can we really do one task after the other sequentially without having to reset the robot? And actually, this works. So I mean that the view is not great. I don't know if I can maximize this. But basically here, we're first doing one of the tasks, then we're just changing the object in the scene and also the language command to the robot, and then it would figure out on its own that it has to activate a different adapter, which is like shown here. And then finally, again, we instruct the robot to just close the drawer, and this is what it would do. This also works when we do this before the first task is even completed. So here, right in the middle, basically, the robot was starting to do the first task, and we just changed the language instruction, and it was moving away to perform the other task of closing the drawer. And because in the real world, we could only do 5 experiments, 5 different tasks. In simulation, we also did many more. So this is, for example, for 10 tasks, but actually I'll show in a bit that we tried this for even more tasks.
And then just in the previous videos, it's not understanding correct that the point you're making is it's not just vision conditioning.
Yes, like it's actually doing both. Yeah. And also not. Yes. I think this was the main point.
Great. Then keep going. I'm just going to open the door for the pizza. Yeah, come on.
And because the reviewers also asked for this kind of experiment, which is also why we did it. We didn't think about it in the first submission. Okay, so yeah, to also show some quantitative numbers. So this is basically showing some of the simulation results that we got. So here you can see in red, we have performance on task 0 at different stages. And as soon as we learn the task, of course, performance goes up. But then with our method, performance actually stays high, whereas with also the baseline, it decreases quite quickly. And yeah, the main point is here that we can kind of retain this high performance on newly learned tasks while learning all the subsequent ones. Yeah, also here some numbers. Basically, there are 3 metrics common in continual learning. Basically, this here quantifies the degree of forgetting, and you can see that it's a very low number, which is good. So 100 would be the forgetting, and 0 is no forgetting. Yeah, so here we have some ablations on. Yeah, I'm not sure. Basically here, we vary the threshold for adding new adapters to the model. As I showed before, we have some line, if all the losses are above this line, and then we don't expand the model, and we can of course increase or decrease this threshold. And if we choose this to be at a higher level, then we can see that the new adapters that we add actually get less and less, because because as I showed before, you saw the plot. If we do this, if we add less adapters to the model, then of course the capacity of learning new tasks also decreases a bit. And you can see that the performance on new tasks goes down a bit. It's because we add less parameters to the model. And this I think was a really cool result about which I was quite happy. So here we scaled this to 40 tasks in simulation. We could basically, at the final stage, we have one model that can do all these 40 tasks that it has learned one after the other, without basically okay, this is actually CLARE. So here you can see the performance doesn't really go down, versus if you use experience replay, basically you just train on all the data that you've already collected. You can see that for some tasks, like this one, or even the first one, performance is quite high at the beginning, but then it goes down very quickly and stays very low. So then maybe a few more details about the reward tasks. These are the ones that we considered. Not too complicated manipulation tasks, but the main point was to show that this continued learning actually works in the real world. And here we didn't compare against all the baselines from the simulation experiments, but here we could also see that basically the same story as before. This negative backward transfer, of which quantifies forgetting, was very low. Okay, and another cool aspect is that, as I said at the beginning, it's quite parameter efficient. So the parameters only increase about 2% per learned task compared to the number of parameters of the base policy. This can of course be a bit different if you have another policy, but in principle, these adapters are intended to be act, because they also don't need to learn so much. They just need to learn to kind of correct what the pre-trained VLA would do, which is often not. It's much easier than learning from scratch how to operate a robot in the real world.
Maybe a question for the model that you used. If you used a task over batch sampler, how much forgetting would then happen? You have your pre-training. Maybe during the pre-training phase, you have this batch over task over batch sampler. You're training. Compared to that, how good is the quality? Or if you
when you do it in pre-training, you have a task aware, and then but when you fine tune, in our case, we assume that we don't have access to all the previous data. That was that was a key. Okay, I should have mentioned this in the beginning. The idea is, of course, if you have access to all the data that your model has already seen, then you could just kind of learn something new. You can replay this and inject it a bit into your training mix. But we assume that when you have a robot that's really deployed for months or years, we cannot just store all the data that this robot has ever been trained on. Also, and because of privacy, if you would really have a robot like this in your home, and then you sell it to someone else, I think you can also not count on being able to access all the data that this robot has seen maybe at a different home. So I think because of storage and maybe privacy restrictions, we did assume that. We assume that we did not have this access. Okay, so finally, this is our lab at UM. I don't know if there are some master students around here, and please feel free to check out what we do. Maybe join us.